Good morning, all of you. In this session, I am going to explain about 4 simple problems on Goodman and Soderberg methods. In yesterday class, already we discussed about Goodman method for combination of stresses. This Goodman method is designed based upon the ultimate strength, ultimate stress. Okay, Goodman's method designed based upon the entrance limit and ultimate stress. Okay, and this is the derivation for Goodman's expression. Okay, already explained in our previous class. And also I explained about Soderberg method. Soderberg method mainly depends upon entrance limit and yield stress. Okay, the design mainly depends based on yield stress and entrance limit. Okay, this is the derivation for Soderberg method. Okay, this is the formula for Soderberg equation. Okay, I already explained it in previous class. Okay, now these are the important formulas used in our second unit. Okay, this is the Goodman's equation. Okay, if you are considering theoretical stress concentration factor and fatigue stress concentration factor here, then you have to multiply KT and KF values. Now here K load, K size, K surface, K miscellaneous are the factors affecting the fatigue stress concentration. K load is the load factor, size factor, surface finish factor, and miscellaneous factor. Okay, KT is the theoretical stress concentration factor. KF is the fatigue stress concentration factor. Okay, here sigma m is the mean stress, mean or average stress. Sigma u is the ultimate stress. Sigma e is the entrance stress or entrance limit. Sigma v is the variable or fluctuating stress. Okay, now this is the formula for Soderberg method. Here the main difference for Goodman's method and Soderberg method is sigma u and sigma y. Here we are considering sigma u. Here we are considering sigma y. This is the main difference between these two topics. Okay. Similarly, if you are considering KT and KF values, then the equation is like this. Okay. Just you have to replace this sigma u with the sigma y. Okay. This is the main difference between Goodman's and Soderberg equations. Okay. If you are considering the torque or torsion or shear stresses, then the equation is 1 by Fs equal tau m by tau u plus tau v by tau e. Tau is the symbol for shear stress. So mean shear stress divided by ultimate shear stress plus variable shear stress divided by entrance shear stress. Okay. Now if you are considering theoretical shear concentration factor, okay, fatigue shear concentration factor KFS, then the formula is like this. Okay, here tau m is the mean shear stress, tau u is the ultimate shear stress. Okay, tau e is the entrance shear stress, tau v is the variable shear stress. Okay. For Soderberg method, the formula is the same. Okay, 1 by Fs equals tau m by tau v plus tau v by tau e. Okay, just you have to replace tau u with tau y. Okay, and this is the same expression for Soderberg. Okay, now these formulas are very important for our design problems. Okay. Please all of you remember these formulas. Okay, Now, by using these formulas, I'm going to explain some problems on Soderberg and Goodman's method. These are the formulas for mean and variable stresses. Now, W max is the maximum load, W minimum is the minimum load, then average or mean load equal to maximum plus minimum by 2. Now, for a variable load, W variable equal to variable load equal to maximum load minus minimum load by 2. Okay, these are the formulas for load. If you are considering stresses, then sigma max is the maximum stress, sigma minimum is the minimum stress. Then mean or average stress equal to sigma max plus sigma minimum by 2. Okay, maximum stress plus minimum stress by 2. For reverse stress or variable stress, then sigma variable or sigma V equal to maximum stress minus minimum stress by 2. Okay. If you are considering torque, okay, if you are considering a torque, then T max is the maximum torque, T minimum is the minimum torque, and average or mean torque equal to maximum torque plus minimum torque by 2. For variable torque, TV equal to maximum torque minus minimum torque by 2. Okay. If you are considering shear stresses, then tau max is the maximum shear stress, tau minimum is the minimum shear stress, average or mean shear stress equal to maximum shear stress plus minimum shear stress by 2. And variable shear stress, tau variable equal to tau max minus tau minimum by 2. Okay. If you are considering bending moments for determining the value of the bending stress, sigma m max is the maximum bending moment. M minimum is the minimum bending moment. For determining the mean bending moment, then m equal to m max maximum bending moment plus minimum bending moment by 2. For determining the value of variable bending moment, then mv equal to maximum bending moment minus minimum bending moment by 2. Okay, these are the important formulas for determining the mean and variable values. Okay, and these are the another formulas. Okay, this is the formula for shear stress. This is the formula for shear stress, solid and hollow. Okay, this is the torque for solid shaft. This is the torque for hollow shaft. Okay, this is the bending stress for a solid shaft, bending stress for a hollow shaft. Okay. Now coming to the first example, the question is a machine component is subjected to a flexural stresses which fluctuates between plus 300 megapascal and minus 150 megapascal. Then determine the value of minimum ultimate strength according to Gerber method, and modified Goodman method and Soderberg method. Take yield strength equal to 0.55, ultimate strength 0.55 times the ultimate strength. Endurance limit equal to 0.5 times the ultimate strength, and factor of safety equal to 2. Okay, this is the question. From this question, you have to find out the value of ultimate strength. Okay. So here you can observe, you have to find out the value of ultimate strength according to Gerber method, modified Goodman's method, Soderberg method. Okay. So here the given data is maximum and minimum stresses are given. Here 300 megapascal plus 300 megapascal is the maximum stress. Minus 150 megapascal is the minimum stress. So from given data, sigma max equal to maximum stress. Okay, megapascal, 1 megapascal equal to 1 pascal equal to 1 Newton per meter square. So sigma max equal to 300 and sigma minimum equal to minus 150. This is the maximum stress, this is the minimum stress. And here take yield strength. Yield strength means yield stress. Sigma y equal to 0.55 times the ultimate stress. So sigma y equal to 0.55 sigma u. Okay, and entrance stress sigma e equal to 0.5 times the ultimate stress. Okay, entrance stress equal to 0.5 times the ultimate stress. Okay, so sigma e equal to 0.5 sigma u, and factor of safety fs equal to 2. Okay, this is the given data. By using these details, you have to find out the value of ultimate stress sigma u. Okay, here sigma u is the ultimate strength or ultimate stress. First, you have to find out the value of mean and variable stresses. Okay, sigma max is the maximum stress, sigma minimum is the minimum stress. Now, then already we know that formula for mean stress, mean or average stresses, sigma mean equal to maximum stress plus minimum stress by 2 is the formula for mean stress. Substitute the values of sigma max and sigma minimum in this equation. You will get the value of mean stress sigma m. Sigma m or sigma mean equal to 75 megapascal. Okay. Now, from the formula of variable stresses, sigma variable equal to maximum stress minus minimum stress by 2. Okay, from this equation you can get the value of variable stress sigma v, that is 300 minus of minus 150 equal to 225 megapascal. Okay, this is the sigma m, this is the sigma v. By using these two values, you can determine the value of the sigma u by using 3 different methods. First method, according to Gerber method, according to Gerber equation, 1 by fs equal to sigma m by sigma u whole square into fs plus sigma v by sigma e. Already we determined the value of sigma m. Sigma m equal to 75, sigma v equal to 225. Okay, and the value of sigma u, we have to find out the value of sigma u, and the value of fs is given, that is number 2. Value 2 is the fs value, and the sigma e is the 0.5 times the ultimate stress. Okay, so from this equation you can determine the value of sigma u. Okay, so sigma u equal to 924.35 megapascal. This is the final value for ultimate stress according to Gerber equation, according to Gerber method. Okay, now according to modified Goodman method, this is the formula for modified Goodman's method. 1 by fs equal sigma m by sigma u plus sigma v by sigma e. Sigma m is the mean stress, sigma v is the variable stress. Already we determined the value of sigma m and sigma v. Sigma u, we have to find out the value of sigma u. Sigma e is the entrance limit equal to 0.5 times the ultimate stress. Okay, substitute the values of sigma m, sigma v. From this equation you can get the value of sigma u. Okay, here sigma u equal to 1050 megapascal by using Goodman's equation. Okay, this is the final value for ultimate stress according to Goodman's. Now, according to Soderberg method, already we know the equation for Soderberg. 1 by fs equals sigma m by sigma y plus sigma v by sigma e. Just substitute the values of sigma m, sigma v, sigma y, and sigma e. Okay, from this equation you can get the value of sigma u. Okay, the final answer is sigma u equal to 1172.72 megapascal. Okay, this is the answer according to Soderberg method. Now coming to the other example, a bar of circular cross section. Here, a bar of circular cross section. Circular cross section. That means the cross section area of a specimen is given. That is in circular shape. Okay, cross section is circular shape. Is subjected to alternating tensile forces varying from minimum of 200 kilonewtons. That is here the units is newtons. That means it is load. 200 kilonewtons is the minimum load, and the maximum load equal to 500 newtons. It is to be manufactured of a material with an ultimate tensile strength. Ultimate, that means sigma u equal to 900. Sigma u equal to 900 megapascal. Okay, sigma u equal to 900 megapascal, and entrance limit, that is sigma e equal to 700 megapascal. Determine the suitable diameter of the bar using safety factors 3.5 related to ultimate tensile strength, 4 related to entrance limit. A stress concentration factor of 1.65 for fatigue load. Okay, use Goodman straight line as basis for design. So in this problem, you have to consider Goodman's method. Okay, these are the given values. From given question, minimum load equal to 200 kilonewtons. Okay, 200 kilonewtons is the minimum load, and maximum load is 500 kilonewtons. Okay, and ultimate stress sigma u equal to 900 megapascal, and entrance limit sigma e equal to 700 megapascal. Here factor of safety are given. Fs for ultimate stress. Fs for ultimate stress equal 3.5. Factor of safety. Fs means factor of safety for ultimate stress equal 3.5. Factor of safety for entrance limit, that is FSE equal to 4. Okay, stress concentration factor KT equal to 1.65. Fatigue stress concentration factor KF equal 1.65. And here from the formulas, W max equal to 500 maximum load, W minimum equal to 200 kilonewtons. Already we know the formula for mean load. Mean load equal to maximum plus minimum by 2. Wm equal to maximum load plus minimum load by 2. So here the mean load equal to 350 kilonewtons. That means 350 into 10 power 3 newtons. And variable load W variable equal to maximum minus minimum by 2. That is 150 kilonewtons equal to 150 into 10 power 3 newtons. Okay, these are the mean and variable loads. By using these mean and variable loads, we have to find out the values of mean stress and variable stress. Okay. So here the cross section is circular. That's why I'm taking area, cross section area A equal to pi by 4 d square. Okay, pi by 4 d square is the cross section area. Okay, so here you have to find out the value of diameter, suitable diameter small d. Okay, capital A is the cross section area of a circular bar. Okay, so already we know that formula for stress equal to load by cross section area. So for determining the value of mean stress, then you have to use mean stress sigma m equal to mean load by cross section area. Mean load equal to 350 into 10 power 3 divided by cross section area equal to 0.7854 d square. Okay, now this is the value for mean stress. And variable stress sigma v equal to variable load divided by cross section area. Okay, this is the value for variable stress. Okay, by using these two values, you have to find out the value of suitable diameter small d. From Goodman's equation, already we know that Goodman's equation, that is 1 by Fs equals sigma m by sigma u plus sigma v by sigma e, is the Goodman's equation. Here Fs value is given for ultimate and entrance limit. That's why here you can observe factor of safety for ultimate stress, factor of safety for entrance limit. Both are given. Then you have to cross multiply this Fs value. Okay. So then Fs, this is the Fs for ultimate, this is the Fs for entrance. Then substitute the values of sigma m. Sigma m equal to 446 into 10 power 3 by d square. Sigma u equal to 900. Fs u equal to 3.5. Sigma v equal to 191 into 10 power 3 by d square, and sigma e equal to 700, and Fs e equal to 4. Okay, here you can observe from this equation you have to find out the value of diameter. Okay, so diameter d equal to 62.9 mm, that is nearly 63 mm. So the minimum size of a shaft, required size of a shaft equal to 63 mm is sufficient. Okay, so this is the final answer for this problem. Okay, now coming to the another problem. Determine thickness of a 12 centimeters wide uniform plate for safe continuous operation. Here you can observe the cross section. The cross section is rectangle. Okay, here the object is rectangle. So the thickness of the object, the thickness of the rectangle is 12 centimeters, and the width of a rectangle is W. Okay. Sorry, here you have to find out the value of thickness T. So here you have to find out the value of thickness T, and width is 12 centimeters. Okay. If the plate is to be subjected to a tensile load that has a maximum value of 250 kilonewtons. So here the units are in newtons. That means it is a load. So it is maximum load, it is minimum load. Maximum load equal to 50 kilonewtons, minimum load equal to 100 kilonewtons. The properties of the plate material are as follows. Entrance limit, that is sigma E. Sigma E equal to 225, and sigma Y, yield stress, sigma Y equal to 300, and factor of safety, Fs equal to 1.5. Okay. From the given question, width of a plate equal to 12 centimeters, that is 120 mm, and maximum load equal to 250 kilonewtons, and minimum load equal to 100 kilonewtons. Okay, entrance stress equal to 225, and yield stress equal sigma Y equal to 300 megapascal. Fs, factor of safety, equal to 1.5. Here T is the thickness of a rectangular plate. You have to find out the value of T. Now already we know that cross-sectional area for rectangle A equal to width into thickness. Okay, width is 120 mm and thickness is T. Okay. Now from the given loads, maximum load equal to 250 kilonewtons, minimum load equal to 100 kilonewtons. Already we know the formula for mean load. Mean or average load equal to maximum load plus minimum load by 2. The answer is 175 into 10 power 3 newtons. So mean load equal to 175,000 newtons. Now variable load or fluctuating load, W variable equal to maximum minus minimum load by 2. Okay, so 75,000 newtons is the variable load. Okay. Now you have to find out the value of mean and variable stresses. Okay, mean stress equal to mean load by cross section area. Here the cross section area is 120 into T. Mean load equal to 175,000 newtons. Okay. Now variable stress equal to sigma V equal to variable load by cross section area. Variable load is 75,000 and cross section area is 120 T. Okay. From this, from these two values, you have to find out the value of suitable size of a thickness. Okay. From Soderberg or Goodman's, we can find out the value of T from Soderberg or Goodman's. Okay. So according to Soderberg's formula, 1 by Fs equals sigma m by sigma y plus sigma v by sigma e is the formula for Soderberg. Okay. Substitute the value of sigma m and sigma y, sigma v, and sigma e. Here you can observe from this equation, you can find out the value of thickness T equal to 11.46 mm. That is nearly 11.5 mm. Okay. So the required minimum size of a thickness T equal to 11.5 mm is the minimum thickness of a plate. Okay. Now coming to the another problem. Determine the diameter of a circular rod made of ductile material with a fatigue strength. Complete stress reversal. Endurance stress sigma E equal to 265 megapascal and tensile yield strength, that is sigma Y equal to 350 megapascal. The member is subjected to varying axial load from minimum load minus 300 into 10 power 3 newtons to maximum load 700 into 10 power 3 newtons and has a stress concentration factor equal to 1.8. Okay, stress concentration factor equal to 1.8. Use the factor of safety as 2. Okay, from the given question, this is the endurance stress. So this is the endurance stress equal to 265 megapascal. 1 megapascal equal to 1 newton per mm square. So 265 newton per mm square is the endurance stress. And sigma y is the yield strength or yield stress. Yield stress equal to 350 megapascal. So 1 megapascal 1 newton per mm square. And minimum load equal to minus 300 into 10 power 3 newtons. Minimum load equal to minus 300 into 10 power 3 newtons. Okay. And maximum load equal to 700 into 10 power 3. 700 into 10 power 3 is the maximum load. And Kf is the stress concentration factor. Fatigue stress concentration factor, that is 1.8. Okay, 1.8 is the fatigue stress concentration factor. And factor of safety Fs equal to 2. Okay, Fs equal to 2. These are the given values in our question. Okay. From the given data, you have to find out the suitable diameter of a shaft. Okay. Here the cross section is circular. So the area cross sectional area equal to pi by 4 d square. Okay. From the given data, first you have to identify the shape of a object. Okay, shape of a component. Already we know that mean load equal to maximum load plus minimum load by 2. Here the maximum load is 700 into 10 power 3 and minimum load is minus 300 into 10 power 3. Okay. So finally the mean load equal to 200 into 10 power 3 newtons. Mean load, that is Wm. And from the mean load you have to find out the value of mean stress. Sigma m equal to mean load by cross section area. Okay. So mean load equal to 200 into 10 power 3 divided by cross section area equal to 0.7854. Okay. So this is the mean stress. Mean stress in terms of diameter d. Okay. Similarly, variable load equal to maximum load minus minimum load by 2. So here maximum load 700,000 minus 300,000 divided by 2. The variable load is 400 into 10 power 3 newtons. Okay. Now already we know the formula for variable stress. Variable stress equal to variable load by cross section area. So variable load equal to 400 into 10 power 3 divided by cross section area 5 by 4 d square. Okay. So this is the value of variable stress in terms of diameter. Already we know the equation for Soderberg or Goodman's. Okay, you can take any method, Soderberg or Goodman's. Okay, you can take any suitable method. Here I consider Soderberg method because the value of sigma y is given. Okay. So substitute the values of sigma m, sigma v, and sigma y, sigma e. Then you can get the value of diameter, suitable diameter d. The value diameter d equal to 100.5 mm is our required size of a shaft. Okay, so this is the answer for this problem. Okay. Okay.